Hi, in this video I'm going to show one of the two Sereca pilot applications, namely RiskBuster. RiskBuster is a monitoring application for a particular critical infrastructure, which is a water supply infrastructure that must provide secure data communication, secure storage of recent data, secure storage of historical data, reliable reporting to human operators, and also and finally secure and timely detection of anomalous situations. The application is built as a microservice application. It runs on top of a cloud infrastructure and integrates most of the Sereca developed components that leverages Intel SGX technology to provide a strong level of security, even against malicious insiders. There are different microservices in charge of dedicated functionalities and responsibilities. A microservice located on the DEM is the one that collects data from a sensor's data logger and sends this data to the cloud. Data is collected, is sent to the cloud, and then it is exchanged by the microservices at cloud level through the usage of the Vertex Sereca application framework, which is a secure version of the well-known microservice framework called Vertex. The secured version of Vertex runs on top of a Zookeeper cluster manager, which is a particular version of Zookeeper known as a Secure Keeper. Such a version of Zookeeper uses SGX to ensure security of data exchanged by the cluster manager. There are three microservices that uses another Sereca component, which is a SGX-JNI bridge. Such a bridge allows to execute sensitive code in an SGX enclave, even for applications written in Java. The alarm management system, known as that from now on I will call as AMS, is the one that correlates data and performs mathematical operations. The other two microservices, that is the time recent data service, and the historical data service, stores respectively time recent data and historical data within a secured version of storage systems, which are Secure MongoDB and Secure MySQL. These storage systems run in a scone container. Scone is another component provided by the Sereca project, which is a particular version of container that uses SGX to ensure in a transparent manner security to a legacy application. So the archivers, the two archiver microservices, sends the data acquired from the event bus, from the bus of Vertex, and establishes a TLS communication with the secured storage system in order to also ensure the security of the communication between the microservice and the final storage system. The data clearly needs to be sent to a final operator. This is done through a web proxy microservice. This web proxy runs on top of another Sereca component, which is the SGX-LKL, that allows to execute a Java code in a transparent manner within SGX. Finally, it must be said that RiskBuster uses another Sereca facility, which is the Geo-locality functionalities that allows to provide a high level of availability for specific microservices. The Geo-locality feature provided by the Sereca Vertex is organized as follows. We have three different alarm management microservices that runs in three different countries. One in England, one in Germany, and one in Italy. The one in Italy is the one with the highest priority, since it is the nearest one to the critical infrastructure. The other two are the two microservices that runs as a backup solution. So when the AMS in Italy goes down, the other two are ready to take place to become the active one, and so substitute the failed microservice. The demo that I'm going to show wants to demonstrate the operation of the SGX-Secured geolocal alarm management system. You will see that the Italian AMS, having the maximum priority, will receive data from the DEM and correlates such data in order to send the status of the infrastructure to the final operator. The MS performs these correlation functions within the SGX enclave, thanks to the SGX JNI bridge that I showed you before in the description of the architecture. So the status of the infrastructure is then securely sent to the final operator through the web proxy microservice. And then we assume that a failure of the Italian AMS occurs. You will see that when the failure of the Italian AMS occurs, the AMS located in England will become the active one, and so will replace the failed microservice and will keep providing the status of the infrastructure to the final operator. Let's better explain the demo. Data is collected on the dam infrastructure, on the water supply infrastructure, from a sensor data logger. Is then sent by the data collector microservice to the AMS in Italy. The AMS in Italy asks to the time recent data manager microservice some data that he needs for data correlation purposes. Furthermore, the AMS sends to the final operator the status of the infrastructure and signals eventual alarming conditions happening on the infrastructure. Then, if the AMS in Italy fails, the AMS in England becomes, which is the one with the second priority, becomes the active one and sends the status of the infrastructure to the user operator, and so it is able to keep the updates of the status of the water supply infrastructure continuously in the time. All right, let's see the demonstration. At the top of the screen, we have two terminals connected to the Cloud Metal as a Service in Germany. I will use the terminal on the top left to run most of the microservices at cloud level, and the terminal on the right, I will use the terminal at the top right to run the AMS microservice located in Germany, which is the one that also runs at the cloud level. At the bottom, we have other two terminals, one from which you will see the AMS located in Italy running, and the other one on the right that will be used to start the AMS microservice in England. So the first thing I'm going to do is to start the AMS in Germany, and then start the core part of the application. So for example, the other microservices like those dedicated to the storage systems, the web proxy microservices, and others. The application now is running, and you can see that the AMS in Germany is the one that now receives data from the infrastructure and sends the status of the infrastructure to the final operator. As soon as the one in England with the second level of priority starts, the one in Germany will stop running, and the AMS in England becomes the active one and receives the data from the cloud. The same applies when I start the AMS located in Italy, which is the AMS with the highest priority. And so the AMS in Italy is the active one and correlates within the SGX enclave in a secure manner all the data received by the critical infrastructure. In terms of graphical user interface, the final operator will have such a graphical user interface from which he can monitor in real time the status of specific sensors, like temperature sensors, water level sensors, flow meter sensors, turbidity sensors, and so on. And then he can also receive the status of the infrastructure, eventual alarming events, and also the situation of the alarm management system geolocation system. As soon as a failure of the microservice in Italy occurs, the AMS in England substitutes that failed microservice and becomes the active one. And the final operator, the user operator, is aware of this, since the graphical user interface shows to him that the alarm manager in Italy went down, and also that the active microservice is located in England. Hope you enjoyed. Thank you.